It's a pleasure to be back after 2 weeks of absence in Brussels, and it's a real pleasure to be in this beautiful room from the Academy, so thank you very much. So, as Pierre said, my name is Mathaios Panteli. I'm an assistant professor at the University of Cyprus. I also hold a position at the Imperial College London. So I will give a brief introduction to myself for those who may not have been in the first lecture. Those who have been in the first lecture, please bear with me for a few moments. My background basically is purely on electrical engineering and primarily on power engineering. So I did my diploma in Greece, in Thessaloniki, in the north. Then I did my PhD at the University of Manchester. And then I switched between Cyprus and Manchester for some years as a postdoctoral research associate before becoming a lecturer in power systems at the University of Manchester for about 4 years. And then I moved in January 2021 back in the University of Cyprus, where I'm from as well originally. So this is a very brief background. So an overview of the lectures. So we had the first lecture back in 2 weeks ago, on the 11th of March, where we basically reviewed together some of the work we did in different projects on quantifying resilience, using different measures for different threats that we've seen together about windstorms, floods, earthquakes, fires, and so on. So the idea in this lecture today is to see basically how we can leverage that understanding of quantifying resilience with different metrics and put that into planning to see how we can basically plan the system to be more robust to high impact, low probability events. And there are 2 more lectures coming in April and May. The third one will be on cascading and dynamic resilience assessment. So we move from the static impact assessment we did in the previous lectures and today, and then we move on to see how we develop different computationally efficient cascading simulators and how those are applied to basically the future renewable rich power systems. And then we'll close with a lecture on the flexibility in sustainable energy systems, looking at multi-sector and multi-vector next perspective. So not looking only to the electricity infrastructure sector, but also how coupling with other sectors such as water, transportation, and different multi-energy carriers can complete the picture of future resilient power systems. So over the years, again, I would give a brief overview of the projects we did. Over the years, we worked on different projects in different areas around the globe, starting from UK, of course, where I was originally based as a PhD researcher, postdoctoral, and also as a lecturer there. So we started the first project in UK looking on resilience, which was a project called ResNet, where we developed basically the fundamental understanding of the work we did over the last decade. So ResNet was basically the initiating point, if you like, of our work on the topic. It was the first project in UK as well that was actually funded and organized as well by network operators to look into this problem. Then building on ResNet, we were successful in securing more projects. This one was with a collaboration with Chile, where basically it was funded by the Newton Fund, which was a fund aiming to bring together different countries from the developed and developing world to solve basically global challenges. And were awarded with the 2018 Newton Prize for the impact that the project had on Chile, which was about assessing and enhancing the resilience of the transmission network there to earthquakes, which I will give more implementation illustrations later. Then we also had a project looking at landslides and floods in Malaysia, which I will go into more details again later in the presentation. We completed a couple of years ago the Forward Resilience Measure project, which was a follow-up in a way with some years of difference of the ResNet project. But this project was very successful because it brought really resilience in the agenda of Ofgem, the electricity regulator in UK, and now we're having a follow-up project as well as we speak. We also looked a bit at the compound risk analysis, looking at cyber and physical threats. I was more into the physical resilience assessment in this project that was funded by the Department of Defense in United States, where we're looking basically at the cyber and physical integrity of the Oahu Island in Hawaii. And currently, we're involved and we're leading a product in the R22 project, which is organized by ETRA in Spain, where we're looking basically and developing different products, as you may see from far in this diagram here, where we're basically responsible for the C3PO product, which is looking at multi-risk assessment frameworks for power systems, looking both at cyber and physical analysis. Also, currently we have the HVNDC-WISE project, where we're trying to understand the role of HVNDC links into acting as firewalls into the cascading analysis. And this is something I will be talking much more in the next lecture, where we basically plugged different DC technologies into our dynamic cascading simulators to see how the future AC/DC systems will respond to large disturbances and to big cascading events. And we also have the wellness project, which is currently running now, which is taking basically a holistic whole energy system perspective into the vulnerability of electricity systems in UK. And we're looking from the TSO perspective, from the DSO perspective, and also the TSO and DSO analysis. We're trying to develop what we call the stress tests for the electricity infrastructure of UK, and then how we can bring that into the cost-benefit analysis in order to basically define the pricing mechanisms and the economic incentives from Ofgem to the network operators to further strengthen their robustness to extreme events. Okay, so before going into details on the presentation, I thought to refresh a bit what we said in the previous presentation to give some context, because everything is related. So the definition of resilience that we defined in the CIGRE working group C4.47, which Pierre was involved as well, we define resilience as the ability to basically limit the extent, severity, and duration of system degradation following an extreme event. And within this definition that we had, and there are literature online that you can read much more about the definition, I don't want to go again into details. We define basically what we mean by each word in this definition. So we define what we mean by extended severity. So we refer to the geographic extension, to the intensity of the event. The severity of the event, we basically dealt only with events that had actually an impact and consequences of the system. And we also define what we mean by degradation and what we mean by extreme event, and how that relates basically to the standard definition of ENTSO-E in Europe, that basically is out of ordinary contingencies that might happen in power systems. And what we also did, we compared resilience and reliability. Pierre might remember that we had very long discussions on how the different concepts relate to each other. And this is a table basically that tried to summarize the comparison between the two, which again, I don't want to go into much details, but they are fundamentally different in scope. And here we try basically to categorize these differences into what contingencies they're considered. So looking basically resilience, it can be whatever event, it can go up to n minus k event, where k might be a number of assets that tripping in a very short period of time, where reliability is more into n minus 1 or n minus 2 security analysis. When it comes to performance of the system, under the reliability concept, basically you are not expecting any big cascade, or should not be expecting any big events. While in the resilience idea, you actually appreciate and you acknowledge that you have a partial or total system collapse, and hence some consequences on your system. And then another important thing is the system restoration, which we're discussing earlier today as well with some colleagues in the room, comparing reliability and resilience again, which is much longer because your infrastructure is damaged. Compliance to regulation, which is a big thing now in industry. So basically how you can embed resilience into your decision making and into basically your standard, your network operating and planning standards to withstand big events. And then the interdependency between different infrastructures, because we notice that when there is a big event, it doesn't stop only in the electricity sector, but it propagates, of course, to many interdependent systems. So when it comes to the question if we can keep the lights on, whatever happens, this is again from the previous presentation. So we have what we call the reliability paradigm, so the state of the art as we're doing things traditionally. So under the security and adequacy definitions by Ron Allen and Ron Billiton, if you are fans of those two specific academics, as I am. So basically on the one hand we have the adequacy generation, so we're trying to basically have enough generation in the system to meet the demand. And we also have the security definition where we basically need to operate the system in a way to withstand any N-1 or N-2 conditions depending on the country you are. So in UK it's N-2 because most of the lines are double corridors. So in the reliability, let's say, paradigm, we simply put, we need to keep the lights on whatever happens at all times. So when we have the resilience paradigm, however, as I said earlier, we need to expect some performance degradation. The important thing is to maintain basically a critical system operation in order to enable the quick recovery. So you expect your system to degrade in its performance, but there are some standards and there is a trend, of defining this kind of minimum system operation that you need to have in order to enable your quick recovery. So you acknowledge that you have an impact, but then you need to make sure that you don't degrade to an extent that your recovery will be much, much slower. So in the literature, there's this discussion if basically we have the N-1 or N-2 reliability criterion versus the N-K resilience criterion when it comes to the resilience paradigm. So putting this mathematically, hello, no problem. So putting this mathematically, to see, this is what we'll be using later on in this presentation. So if we have this probability distribution of a performance indicator, let that be, for example, energy not supplied in this example, we have the probability on the y-axis, and then we have the performance indicator in the x-axis. So if you simulate thousands of events, as we'll see later in the presentation, you can get, with different probabilities, different intensities, and so on, you can get what we call a heavy tail probability distribution. So you can see that basically there is a heavy tail, a long tail, where we have here the high impact, low probability events. So traditionally what we've been doing and what the regulation and the network standards are based on is on the mean value or the expected value of a performance indicator. So you have, for example, 100 events, you quantify their impact, or you have their impact based on the historical data, and then you take the average of those events, the average ENS that occurred, for example, in those events, and then you try to basically design your system to withstand that average. This, however, neglects this kind of tail that we have in this heavy-tailed probability distribution, and what we call the tail risks. Because if you take, for example, if you assume that you have 100 events, 90 or 95 of them will be ordinary or average, and then the other 5, which will be summed up and averaged in this thing, will be actually your high impact, low probability events, which is what resilience is all about. So the idea is basically to complement the traditional reliability-oriented planning with the resilience aspect, and to find a solution that can basically achieve a trade-off between your day-to-day operation and your operation during extreme events. And this is a particular picture that I like when we're talking about average values for resilience and high impact, low probability events, where basically this shows a statistician that drowned while crossing a river, which was on average 3 feet deep. So you can see that basically is what we have in our analysis, if you like, these high impact, low probability events, which goes beyond the average expectations. So as I said, as we said in the previous lecture, this is a limitation in current regulatory standard, and it's something that we're pushing from our community with regulators in UK as well as in Europe, in order to basically take this kind of conditional values, the extreme values, into consideration when incentivizing the network operators. Because This is basically some events that happened in UK, where National Grid, as the system owner and operator of England and Wales, they did quite well, and they were performing under the threshold imposed by Ofgem for most of the events, but we can see that there were some events that were exceeding a lot the threshold that was set by the regulator in UK. Now, is it National Grid's fault? It's not, because basically this is what they were regulated against, this is what they were incentivized financially to prepare the system to withstand. So whatever is beyond that threshold, basically you do what you can to survive the event. Okay, I will skip this. So when you're trying to basically decide on an investment option, this work we did with World Bank, which was mainly for developing countries, but it applies to any network at any country. So you do your preliminary risk screening. So you try to identify basically what is stressing and what is actually threatening your system. Then if you can, you do the data-driven risk identification. So basically you try with different climate models to benchmark your analysis, to fine-tune your simulators against observed data in order to have a better realistic quantification of the impact on your system. Then you do the integrated planning, as we'll show in this presentation, and then you do the cost-benefit analysis. The problem with the cost-benefit analysis that the network operators and regulators are quite opposing, let's say, this approach, is how to assign probabilities to all these events. And that's a big challenge because basically we have limited experiences. You can apply different mathematical models to try to quantify the probability of something happening, but it will not be cross-referenced and cross-validated with historical data, which is quite challenging if you want to plug this kind of events into the traditional cost-benefit analysis as it has been done so far. Now there is a more trend towards more probabilistic, more risk-aware approaches, which try to basically mitigate this gap between existing approaches. So very briefly again, so what we did first, we developed different spatial and temporal simulators to basically model first the event on the impact of the event of the system. And this is just an example in Portugal that we did for the Universal project, where basically you can simulate the event as it moves across the system. You can do what we call the fragility assessment in order basically to define the failure probabilities of the affected assets. And then you can get the time series of your network status as affected by the event. And then you can plot different indices, for example, the energy not supplied, as I mentioned earlier. So just looking into a very simple illustrative example of how this works, if we assume we have this 4-bus system, a very simple system, we project that to an area, let's say assuming in Portugal. Then what we do, basically we simulate the event as it moves across the system with the small dots you see on the slides. And what the simulator does, basically, it can identify this intersection point between the event and your asset. So you can have basically the mapping of the event on your infrastructure in order to see exactly how much and at what time step your infrastructure was affected by the event. And then you can use these fragility curves in order to come up with the probability of failure of the event, which you can then plug into whatever model you are using, Monte Carlo simulations, or whatever you are using to use as your sampling and your probability assessment. And the final output would basically be what we see here, where basically would be a temporal and spatial basically assessment of your line status as affected by the event. And because basically in our simulations they were quite computationally expensive, so we're running thousands of scenarios. When we're trying to plug those into planning models, it was getting very, very heavy. So what we also have in this simulator and automatically does, it tries basically to reduce the scenarios that you're considering in your planning. And the way we did this, there are different ways to do that, but we try to keep the statistical characteristics and in particular the mean and the standard deviation of the scenarios, because we are very much interested in also capturing the mean, but also the tail of the event. So we try to keep the same characteristics in order to be as realistic as possible in our planning later on. Okay, so this is, so the idea, as I said earlier, is when you're trying to improve your resilience and your robustness to extreme events, at the same time, ideally, you would find a portfolio of investments that optimize your performance to day-to-day operation, as those are quantified by the average metrics. So if we look into this probability distribution of event, the idea basically is to achieve an improved expected energy supplied, so the average value of your performance metric, as well as an improved measure of your tail impact, as that is captured basically by the conditional value at risk, which is basically, in a few words, is the average of your very extreme scenarios. So you're trying to basically co-optimize both metrics. Yes, as we had here. So there are many ways of doing that, and it's what we defined as the resilience trilemma in the very first works that we did. So you can make your network more robust to never trip, basically, which is economically very expensive to do. So you can make your network stronger. You can make your network bigger, so you can add more and more redundancy. But as we demonstrated in the previous presentation, that doesn't always work because the redundant elements might trip as well or might be affected by the event. Or you can make your network more flexible and more robust and more responsive to the event. So you add more flexibility in order to find alternative ways for supporting the demand or recovering from the event. And this is basically a figure that actually shows how this kind of loop works in our case, and I will show more examples later on. So you have your longer term planning, where basically after the event, you take all the experiences that you had, you take all the measures you have, and then you put those into optimizers under uncertainty to define your planning strategies. Then you have the operational planning as well, which I will show some examples later, which basically those happen just before the event. So it's ideally you will get a mixture of big expensive investments because you cannot avoid that, but you can complement those big expensive options with more flexibility embedded into your system. Okay, so what we did within the Universal project was building into the previous projects. We built basically an integrated reliability and resilience planning model, which brings together the fragility-based event simulators that we've shown before, the scenario reduction to make it more computationally tractable, and this is thrown into an optimizer basically, which captures also the time domain of your simulations. Our objective function was basically this weighted function, where the objective was to minimize as much as possible both the expected value of the energy not supplied, or again, any metric you may have, and also the conditional value of your metric, which captures exactly the tail of your probability distribution. And we use veta, which veta basically is the weight that you are allocating to your reliability enhancement, as that is reflected from the average metrics, and to your conditional and to the conditional value, as that basically reflects more your resilience enhancement. So we're trying to basically balance the investments between the two metrics, either average or tail enhancement. So to put this into a bit more perspective, what we mean by the different risk approaches that you can have, we basically have three approaches. We have the risk neutral, the risk averse, and the risk seeking approaches. So if we take a look into this simple example, we have, let's say, two options for a consumer. So a consumer can pay $19 for electricity service that hardly never fails, okay? When it does, the impact is small, so there is small ENS, and the associated cost, let's assume, is $10, okay? You also have option two, where the consumer pays much less, they pay $15, but when a disturbance happens, the impact is much bigger, so the cost associated to that is $15. In total, both options are totaling to $100, okay? So 90 plus 10 and 50 plus 50 in the second option. Now in these three approaches, the risk neutral basically is if the consumer is indifferent of the two options, so it can be whatever. Risk averse is basically preferring the first option, where basically you are paying more now in order to mitigate the impact later. And the risk seeking is basically option 2. So they prefer option 2, they prefer to pay less, and then if something happens, we see later what to do, how to recover, how much it will cost, and so on. In our human nature, basically evidence shows that we prefer option 1, because if you think about it, we have insurance for everything. For our house, for our phone, for our car. So we prefer to pay, depends how much is the car insurance in Belgium, 500 euros, 1,000 euros, or 2,000 euros for our car insurance, where if and when something happens, which may not happen, we'll be insured. The same with our phone, and I have my phone insured because I'm really bad with my things. So and I used my insurance, my phone insurance a couple of times so far. So we prefer to pay much more in advance to be safer later in the future. So this is more how this risk-averse and risk-aware approach works in the examples that we see later on. So a simple illustration in the IEEE 33 bus system. So we simulate different 1,000 scenarios. We did this kind of scenario reduction to be more computationally tractable and efficient in our simulators. And then we started playing with this vita value. So basically, just to remind you that we have this vita value where if we put vita equals to 0, it means that we completely, not completely, we don't consider much the tail risks, so the extreme events. If we put vita equal to 1, it's like we're focusing only on extreme events, and somewhere in between is like you're trying to compromise between your day-to-day events and to your extreme events. So when we put that to a test, if we are in the risk neutral approach, so basically vita equals to 0, okay, so we focus more on optimizing the mean values. Here the optimizer decided basically we have 3 options: to harden your overhead lines, to put your lines underground, and to put some batteries to provide some flexibility into your system. So here what the optimizer does, subject to some constraints, some budget constraints of course, they harden a bit the overhead lines, they put more batteries to have more flexibility into your system. While when we go into the risk-averse approach, so basically vita equals to 1, so we focus more on the tail risks. What the simulator does, what the optimizer says, is basically to underground your lines connected to your main grid. So basically you're making your lines 100% reliable to extreme wind events. And then you do a bit of hardening your infrastructure, you have a battery there, and then that basically achieves a better curtail of your tail in your probability distribution compared to what we had earlier here. So the yellow here basically is the events, the extreme events, where if you apply this approach, you see that the distribution is moving more to the left, so we curtail basically the heavy tail. Ideally, not ideally, sorry, I should have said that. When you are trying to achieve a trade-off between the two, this is for vita equals to 0.5, so exactly in the middle. This is more or less the compromise, what we call compromise solution. So you don't maximize or you don't optimize in a way your resilience, neither your resilience or your reliability. So you are having an infrastructure that can, in a way, as much as possible, withstand both credible, your expected events, and not credible, your higher impact events. And just to put this clearer into a table, not looking into probability distributions. So here we have the expected value, and here we have the conditional value using an alpha value of 10%. So consider it basically the 10% worst scenarios that you have. And here we have the base case without doing any hardening into your system. So we have basically approximately 10 megawatt hours as an average of the impact of the event, and you have about 32 megawatt hours for your heavy tail risks. So if we look into the different values of vita, starting from vita equal to 0, where we have the risk neutral approach, vita equals to 1, where we have the risk averse, and 0.5, where we have something in between. So we notice that basically when you do your risk neutral approach, so where basically you are trying to optimize your expected value, indeed the improvement that we see, if we compare these three values here, indeed this is the best performance of your energy supply, so the best improvement. On the other hand, if we do vita equal to 1, so we focus more on the extreme events, you have an improvement on your average values, on your expected values, but it's not the best. The best is basically, as it was expected, the reduction in your conditional value, so the performance of your system under extreme conditions. And the worst improvement, as we said, is the other way around. So when you have the risk-averse approach, the impact is the less on your expected values, and when you have the risk-neutral approach, the impact basically is the less on your conditional values. Something in between is this compromise solution, which basically is not the best improvement neither on your average or your conditional values. It's something in between. It works. So this is basically in different interactions we're having with system operators. This is the solution that it's more likely to prefer because you invest in something and you want that investment to basically be beneficial both in your daily operation as well in your operation under extremes. So the question though, because there are many variables, we have the confidence level, we have the risk aversion level, your budget, what events to consider and so on. So what we did in the Universal project, we ran a full sensitivity study on everything that can affect your decision making. So here we have the expected energy not supplied, so the average value, and here we have the conditional value, again at risk for energy not supplied. And in the axis here we have the budget and also your vita value, so basically how risk averse is your investment planning. And again, same here about CIGRE. So this plane, basically every single point of this refers to an investment portfolio. So in this investment portfolio, by varying basically your risk aware or your risk aversion level, you can actually get what you want. So we don't present one option to the system operator or to the decision-making body, but we say for different risk aversion levels that you may have, this is how your metrics will perform. And then it's up to them to decide how much money they want to spend or how risk averse they would like to be in their planning. And we did the same thing about confidence levels, which I will skip for now. Okay, so to make this more practical to the system operators and to the decision-making bodies, we're in the process now of developing a product which it will be with graphical user interface. It's computationally efficient to some extent, and we're working on improving that as well. So this will be a cloud-based application that we hope to release hopefully by summer or by the end of the year. So you log into the website, you go basically into the landing page where you have some details of how things work. And then you can basically first generate your hazard scenarios. So the end user will have the full flexibility, ideally, to embed their characteristics that they want to have, including the maximum wind gas speeds, their flood levels, the direction of the event, and so on, and depending on their interest and their network. Then basically the idea is also to have this kind of interface where the end user can, so far is these three options that we saw earlier, the undergrounding the lines, hardening your overhead infrastructure, and then including batteries, but we're working on including more options as well. Then you can do a single budget or a range of budget analysis to see how, if you pay a bit less, let's say, how your performance will change. And then you can choose different risk approaches to see how your investments will perform under a risk neutral, risk averse, or a partial risk approach. So currently, I mean, there are different visualization stuff in the platform, so you can see the movement of the event, which part of the system was actually affected because of the event. You can visualize where your assets or your optimal assets from your planning have been placed on your system. So basically, this shows strengthening basically this part of the system, and then adding some batteries here and there on your infrastructure. And then you can get different visuals as well on the metrics that you have, including the average and the conditional value, and a bit of cost-benefit analysis on how much your performance improved when you are exposed to a specific event. So we're hoping to basically have a much nicer, let's say, interface of what this is in the very near future. Okay, I think I will finish in about 20 minutes, Pierre. Okay? We're good, right? Not falling asleep? Okay. Okay, so then moving on to earthquakes, that we did a lot of work in Chile and other parts of the world. So within this scope, we developed an optimization via simulation approach for deciding for network investments for resilience. So it's a two-level optimization. So we have in the first level the optimizer, which basically proposes different enhancements in your system. So that enhancement option is thrown into the simulator, as we explained earlier, but this case for earthquakes, where basically we simulate through very expensive Monte Carlo simulations the system response and the restoration after a random hazard occurs. And then we return basically to the optimizer a resilience metric, and this loop carries on until the best performing option is identified, of course subject to budget constraints. So what you can do with this work, you can basically compare your investment options, and this for the 14 bus system, which is a small application. I will show later for the full Chilean system. We're basically comparing reliability as quantified with the expected values and comparing with the resilience as that is quantified by the conditional values and how your investments change when you're considering reliability or resilience. So we see basically when we're doing the traditional reliability-oriented planning, trying to optimize basically against the average values, the optimizer was giving the obvious, so basically it's adding more redundancy in your system. As we traditionally did things, when we have a problem, we add a redundant asset. While when we're having the resilience improvement, there was a mixture of basically hardening critical substations in the system, so critical central points that you have in the system in order to withstand basically the impacts of the earthquake. But if you put this on a 2D, on a plane, so you can have different Pareto fronts to see basically how your enhancements perform under resilience and under reliability. We also did the same analysis by adding more distributed energy resources in the system to improve the flexibility of the system. Without DG, without distributed generators, again, it's the same picture that we have only hardening substations and transmission lines. But when you actually look into the resilience or the conditional values optimization, we see that already from the third option, we start seeing a mixture between hardening the infrastructure and flexibility solutions. So this basically, within this, what we called earlier, this resilience trilemma, is exactly this illustration. So it's a mixture of infrastructure solutions to make your infrastructure stronger and harder to the event, but also adding more flexibility in order to better recover when you have an event. Okay, so moving on to the Chilean application. So this is the very interesting and nice diagram of the Chilean network. As you know, Chile is a very long country. So the transmission network is like a big radial distribution network. So it seems simple to quantify it and to model, but it actually adds a lot of complexity because of this. So we tested this algorithm that we have on the full Chilean transmission system. And this was before the HVND ceiling was built connecting the north and the south parts of the country, where basically it was bypassing a lot of the bulk transmission system of the country. So this is what I presented in the last presentation as well. So we had this kind of impact assessment methodology where we simulated thousands of earthquakes, as we see in this picture, with different epicenters, with different impact assessment, and we basically were getting all these metrics that we have with what we call the previous presentation, the resilience trapezoid, which we're throwing into the simulator in order to enhance the resilience of the Chilean transmission system to earthquakes. So again, the same comparison for reliability and resilience improvements as we had in the test system before. The number one option was the HVND ceiling in both solutions. Then again, because in Chile there are these substations which are very critical and supporting basically Santiago, Concepcion, and so on in the country, which if they fail or if they collapse, basically big demand centers in the country will fail. So talking also with the Chilean independent system operator in Chile, these kind of investments, so okay, the HVND ceiling, but then hardening your central substation of the country to keep the connectivity of your system is actually what they are expecting to do. And it's what they did as well, in reality, using basically our model. And then it's hardening some key transmission corridors as well of the country. So this refers, so these kind of tables refer basically to individual options of investments. But when you're trying to make a decision, you're looking into portfolios of investments. And when you're looking into portfolio of investments, the one decision can actually affect the other. So what we try to do here for different budget assumptions, we try to see if you have money for one investment, what you do, if you have money for 2, 3, 4, and so on. This is just conceptually, regardless of the actual cost of each investment. So what we see here is that you first do the HVND ceiling to bypass a lot of your infrastructure, which is okay. Then you harden your substations, so combination between DC technologies with hardening of your substations, and then storage comes in the picture. So basically you did your HVNDC, which offers the additional controllability, as we know. Then you harden your infrastructure, but then you also add flexibility. So this is an important note again within this resilience trilemma, that basically it's not enough only to harden your infrastructure, because in the face of a big event, even that infrastructure will fail. So you need to have the means to actually recover as much as possible and as quickly as possible after the event, and is what storage and other flexible solutions provide in such circumstances. So looking to wildfires, I will skip this because this is what we discussed in the previous lecture as well. It's just I put some nice photos here this time, where we see this flying distribution pole, which basically was burned, and then the conductors were holding the pole in the air. This from Greece. We have the spatial model of a wildfire. So this is a very simple example we had in an IEEE Power Energy magazine on a special issue on wildfires. So if we assume that we have the main grid here, and we basically have two cities or areas connected to the main grid with some lines, and then between them with some other lines, and then you have different distribution options in the two areas. And then we assume that this big transmission corridor was basically destroyed from a fire, which is what actually happened in Chile in the big fire of 2020, I think, where basically a big part of the Concepcion area was destroyed from the fire, and the country was cut off basically from the main system. So what we did in this work, we have three cases. We have case A, where basically in case A is a traditional N-1 event. Then we applied that basically criterion to wildfires, where we basically see that we have and big, this is the n-1 criteria, and we evaluated the lowest load cost under n-1. Then we applied in case A, the re-evaluated one. We applied the n-1 security and planning criteria when exposed to fires. So when you are actually applying the same standards for wildfires, we see that the lowest load cost increased significantly because your planning was not, and your system was not designed for this kind of extreme events. And then we had case B, where in case B we actually considered in a probabilistic manner the cost and the impact of the fires, where we noticed basically that more and more distributed energy resources were coming into the picture in order to reinforce the system flexibility. And then we noticed that the lowest load cost was significantly reduced. And then also the operational cost was reduced because you have this kind of cheaper options to serve your demand. So both the operational cost as well as the cost of load shedding was improved when you have a more flexible and DR-rich system. And this is what I also presented in the last lecture, but because it fits nicely with planning. This is what we did for Sarawak, I'm trying to remember the name. Anyway, in the Sarawak Energy, yes, is the electricity utility in Borneo Island. So in this case, we're trying to basically compare different electrification solutions for remote villages on Borneo Island. Where we're basically trying to compare grid expansion with off-grid applications. So we're looking into basically hybrid microgrids for supporting remote areas and remote villages in comparison with expanding the main grid to meet those villages. So if you look into a purely economical analysis, the on-grid transition, because basically you need to invest more to connect the main grid, is of course more expensive compared with the off-grid solutions. And these are just some villages that we considered in our analysis. And this refers to real number because we got all the costings from the electricity utility in the island. So doing the off-grid approach is actually more economically viable. What we did also to see this kind of resilience and sustainability of the on-grid transition into the island, we did this compound risk analysis about floods and landslides. So we had a flood map and a landslide map with associated risks on Borneo Island, which was developed by some colleagues in Newcastle University back then in the project. And we assigned different probabilities and different intensities to the event. And then we're looking into different options to basically expand the infrastructure to meet those remote villages. So the easiest approach was to basically follow the existing roads because that also allows the path to basically build your infrastructure next to the road, and then you follow the road to basically electrify the remote villages. But what we noticed basically with the easiest approach, the easy access following the road approach, is that basically there was a moderate risk of landslide into those streets, into those roads. And indeed there was experience where you have landslides and floods where basically they block the roads. So if the electricity infrastructure was placed into that corridor, it would be severely damaged and then basically would take days or even weeks to reach those remote areas and restore the infrastructure. What we proposed was a different route, which basically you see here that there are no dots. So there are some dots here, but here it was clearer because it was a lower risk of landslides. So we proposed to Sarawak Energy to basically follow this route, so to go up to here, and then to follow this route to reach the northern villages in Borneo Island. And this is what they actually applied some years ago. There were a couple of landslides, not very serious so far. The infrastructure survived, so that was a good outcome of the project. So the villagers there are quite happy with what we proposed. So a few words about a bit of operational planning. So far was on investment planning. We also did work on operational planning. So when you know an event is coming, what you actually do to improve your upcoming performance of your system. So in this work, in the Merge Deep model, which will make open access very soon for everybody to use, we try to basically solve this scheduling problem about mobile energy resources and to dispatch basically these resources into your system, which we try to incorporate basically in optimal power flow. So there have been many works on this topic where basically they make the very rough assumption that you have your depot. So these different points here that we see in the Portugal area, we assume that different warehouses where you have your mobile batteries, which are big containers, or your mobile generators. So what they do basically, very simplistic in different existing works. They assume that if they have, I don't know, somewhere here, the depot, the battery will just go straight into the buses and just connect to the buses and inject energy there directly. But in reality, you have the transportation system, you have the roads, which may be affected, they may be flooded, and so on. So you may need to follow a different route to reach a specific substation in order to connect your mobile resources. So what we did in this work, using Google Maps APIs through Python, we did a multi-layer analysis. So we had the electricity system, and on top of that, we put the transportation system of the country. And then we assumed that basically you have different depots, different warehouses located across the country from where your mobile resources can leave and can go to your main substation. So we have the coordinates of the substations and we have the coordinates of the road in order to go and meet each substation. So this is a very much realistic representation. We also have in the constraints and driving distance and driving speed of a big container to get there. So we have this in a purely and full temporal resolution. And then, okay, here you can see that pink dot moving to somewhere. That's a battery going somewhere. And then it moves around, and then you can see in the time domain how your serve demand changes. And then we tested basically this algorithm for different damages. We assume, because we're not transportation engineers, we assume different impacts basically on the road system and how that affects the performance of the algorithm. But because we assume that we have different depots across the country, so the optimizer basically was able to identify the optimal route depending on the damage on the roads to dispatch mobile resources to go to the different locations in the system. Okay. Also, we did plug different operational planning methods with machine learning to basically make our applications much more realistic. And we developed different close to real-time operational planning actions. So, for example, islanding. So you can island your system if you know that something, a threat's approaching your system, or if you have already some damage. So this can be done in both preventive and corrective modes to split your system basically to self-sustainable islands. So you can basically mitigate the impact of your system to one part and then keep the healthy system operating in order to enable the faster recovery later on. Okay, so I will skip this, I think. Okay, so that was it. So again, on the 17th of April, just to promote the next lecture so you come in the next lecture as well. So we'll be looking, as I said at the beginning, into cascading simulators. And we try to basically bring together what we've seen in these two presentations. So on the one hand side, we will see the impact assessment of big events through cascading analysis. So to see basically how an initiating event from an extreme disturbance can propagate on the system. And we walk through different simulators we developed. And then we will see also cascading driven investment planning. And that is very important because what we do so far, we don't actually consider the cascading into our planning decision making. So we'll see together in the next presentation how we can quantify the impact through cascading and how we can take cascading modeling quantification into investment decision making. Okay? And again, promoting the book that will come soon, hopefully. And thank you very much. Thank you.
So we have